long ago, and it was like.
Okay, folks. Let me say a couple of words about the next homework. I got a couple, I'll start off with a couple of warm ups. Show the following, and get these isomorphisms, you really probably need to use that universal mapping property with the tensor product. It makes life much easier. So you all were asking about some of this stuff here. First, show that when you tensor Q with itself over Z, it's isomorphic to Q, it's a Z module. And show that A tensor B for any R module, A tensor B is isomorphic to B tensor A. Not a shock there, I don't think, but there is a little bit of something to show. So I've got two magical mystery tour problems. And the first one, we want to show argument associativity. So let R be a commutative ring with identity, and A, B, and C be R modules. Find a useful, right, of course, there's always the zero homomorphism now, isn't there? So let's find something useful from the home R, A tensor B, C to home R, A. I think I gave you this one in class last time, part A. So you probably want to, verify to yourself that it's homomorphism and so forth. Find one that goes the other way from here back to here, and then compose F and G in both orders. If you make good choices, good life choices, you should be able to show that these two are isomorphic. And then there's a similar kind of themed problem here with the fact that tensor product and direct sum commute. Here A and B are R modules. Find a homomorphism that goes from A tensor, the direct sum of these BIs, into the direct sum of the separate A tensor BI. And then a homomorphism that goes from the direct sum of the tensors back into A tensor with the direct sum. And compose in both orders to show that these two are isomorphic. So in other words, tensor product commutes with direct sum. So anyway, I think that the theme is kind of similar on all those problems. Any questions on that? Okay, well, let's see. Let me get some light back up here. Let me know if it gets too hot out. It's like hot here. Oh, this thing's got a sticker on it, doesn't it? Oops. All right. If it gets too loud, you can close that up. It's fine to be a little warm in here. Oh, I'm a little dark. Okay, so the last thing that we talked about was this theorem. It was kind of this warm up here. We had R was an integral domain. A is an R module. A and A. R is a domain. A, an R module, and A, an element of A. And we define this crazy script guy here. This is the set of R and R, such that R kills A. Sometimes this is called the annihilator of A. So we had some stuff that we were working on. We showed this A ideal, AT, the set of torsion elements, A and A, such that 0 is a submodule of A. Right. And R mod we proved all this business last time. And what we have left to do is the following. If R is a principal ideal domain, let's see if I can, so one of these works. If R is principal ideal domain, if PIA is 0, that is, so of course what this means, if PI kills A, then that means that the ideal generated by PI is contained in then and if let's suppose that the annihilator of A is generated by that prime power, then Pj A is not 0 for any J that falls short by. Okay, and so what we were left with last time, I think, were D and E. So let's look at that. A, B, C last time. So we want to show that if PIA is 0, certainly the fact that this follows from this is clear, right? Because if PIA is 0, then any multiple of PI kills A. And so the ideal generated by PI must be contained in this, right? Then I claim that this ideal is exactly some prime power, right? Well, notice that this thing is actually generated by X. And this is the assumption that R is a PID. Right? And so the ideal generated by X contains PI, therefore X divides PI. Right? But any PID is a UFD. Therefore, X has to also be a power of J. Right? Because since X divides P to the I, X is part of the prime factorization of P to the I. But there's only one factorization of P to the I, just those powers, or just those I factors of P all repeated. So X is some subcollection of that. Everybody okay with that? Okay, so there we go. PID was important there. Number E, suppose note if PJ A equals 0 for some J less than I, then the ideal generated by PJ is contained in DA, which equals PI. Therefore, PI divides PJ for J less than I which is a contradiction. Okay. Any questions on that? Okay, here is a theorem that I am going to tell you that you may have heard before, or at least in some context. I'm not going to prove it, but I'm going to prove something from which it follows in the finite case. So I'm going to give you the general theorem, and we're going to shore this up a little bit in the finite case. And this theorem is, I think, what you would hope to be true. It's not true in general, but you need a PID for this. Let's suppose that F, well, theorem 13. Let F be a free module over the PID R. Let M be a submodule of that. What are the two things, by the way, just out of curiosity, what would two things be on your wish list for, boy, I hope this is true about M? Also free. Also free, right? That would be super good. And what else? Free modules are described only by the number of copies of R that they're isomorphic to, right? So suppose that R is, suppose that F is some number of copies of R. I would hope that M would be that many copies or less, right? So, and both of these are true. Then M is free, and the rank of M is less than or equal to the rank of F. Yes.
Do we also have that M is a free R mod I or I module where I is a sub where I is an ideal of R?
Yeah, R mod I might not be a domain.
R mod I
In
would
fact, it's usually not.
right.
In fact, if R is a PID and R mod I is a domain, then it's a field.
Right.
Right, so.
But if is M also a free I module?
I is not a ring.
If I is an ideal?
No, we're all talking about unitary stuff here.
Oh, right, yes.
This is true in general. Any module, any free module over PID, I don't care how big it is, right? I don't care if it's got an uncountable base or whatever. Any submodule, if it's over PID. The finite case of this is not too difficult, and I'm going to give you another theorem. When I'm proving this one, I'm going to give you another theorem from which you can get this that I kind of like more. But the case outside the ranking is more difficult, but it's true nonetheless. Before I get started on this other result that I want to prove, I'm going to rip off a couple of corollaries that are worth recording. Corollary. Let's suppose that R is a PID and A is an ungenerated R module. R is a PID and A is an N-generated R module. Then any submodule of A can be generated by less than or equal N elements. B in A is a submodule then B can be generated by notice I don't have the caveat free on this, right? So any random, if you have a module over a PID, then any submodule of that mod, if it's generated by any elements, any submodule is generated by n or less elements. I'm gonna give you one more corollary, and then I'm gonna make some remarks about why PID is important and why some of these corollaries follow. Corollary. Let P be a module over the PID R. Then P is projective if and only if D is free. Okay, so before I move off, it's good to kind of think about some things here. First of all, let me tell you why this result, and this one might be a little bit surprising. I mean, you think, okay, I've got a module, it's generated by some crap. A submodule's got to be generated by less crap. Well, that's not true in general. You might give me an example of an R module that's generated by some number of elements that has a submodule that really requires more elements. And this is what PID is important to. So let me give you kind of an interesting example. Depending on where you had your algebra 1 or whatever's in your class, how many of you have seen an example of a unique factorization domain that's not a principal ideal domain? Right. There's a couple ways you can cook this up, and the easiest way to do this is perhaps this. Here's a down-home, healthy, all-American ring. It is polynomials over the reals in 2 variables. Right? This is pretty easily not a principal ideal domain, because if you look at the ideal generated by XY, this is a maximal ideal. And I can describe what this looks like. This maximal ideal looks like all polynomials in 2 variables over the reals where the constant term is 0. That's it, right? As long as you've got a 0 constant term, that's what this ideal is. And if you think about it, if you've got a polynomial with a 0 constant term, you multiply it by any polynomial, the new guy's got 0 constant term. Because everything's got to at least have a factor of X or Y in it. Everybody agree with that? This ideal is strictly contained in the ring RXY. And let me convince you that this ideal can't be singly generated. Suppose it could, right? This ring is a UFD because R is the reals is a field, RX is a UFD. In fact, it's a PID. And when you take a polynomial extension of a UFD, it's a UFD. So in any number of variables. So this is unique factorization domain. Suppose, just for giggles, that this was generated by a single polynomial, right? That polynomial would have to divide both X and Y. Agreed? So it would have to be of degree 1 or less in X and of degree 1 or less in Y, right? But if it was degree 1 in X, there's no way it's going to divide Y. If it was degree 1 in Y, there's no. So any constant that divides this, or any polynomial that divides both X and Y, has to be constant. It has to be degree 0 in both X and Y. Agreed? But this is the ideal that contains no constant terms. So there's no way that this is singly generated. Everybody on board with that? This is a module, M, that is generated by two elements. It honest to goodness takes two elements. Its ideal is the same thing as a module in this case, because it's properly contained in a ring. This is generated by one, so this is singly generated. And this actually requires two. So this is a submodule. This is a free RXY module, submodule that's not free, and it's generated, and it requires more than one generator. Yes.
So we're, so M is a submodule, is an RXY submodule
Mhm.
of RXY.
Here, the ring R is RXY. That's right.
Sure. Okay.
And actually, I could make this example just more dramatic by instead of taking X and Y, taking X1, X2, X3, X4, polynomial ring and infinitely many variables. And replace this by the ideal that's generated by all the variables. And it's the same thing. Now you have a free, you would have a free R module. And it's got a submodule that can't even be finitely generated, right? So maybe that example might put a little bit of a different complexion on this. 13.1.4, this business about the projective, we already know that free implies projective, right? The other way is true. Can anybody explain why does projective imply free? What's Jim's favorite characterization of projective?
It's the short exact sequence one.
Oh, well, you're tempting me there, Frodo. Yeah, I like that one too, but what, do you remember what's the first one? The characterization of,
There exists a module where the direct sum is free.
so if you have a projective, then you can do this and it's free, right?
Right.
Now look at this theorem. Any projective is a submodule of free and is therefore free, right? Again, you need PID for this, right? So that's why this falls. How about this one about the general? So this theorem says, okay, if you have a free module over a PID, so you're starting with the assumption of free, and you have a submodule, then it's free and the rank is less than or equal to the rank of, yes.
Could you, sorry, you said because it's the direct sum, like that characterization of projective. Then
Yeah,
how does that mean that?
because there's a one-to-one map from P into this, right?
Sure.
So that means that P is a submodule of this,
Sure.
isomorphic to a submodule. And if you have a free module over PID and you have a submodule, then that submodule is free.
Oh, okay.
Okay, so how about this last bit? This one says something a little bit more general. If A is an in-generated R module, and B is a submodule, then it can be generated by a center. Anybody know how we might prove corollary 3.1.3? Let's kind of sketch out why that's true. Let's see, suppose R is a PID. 2, 3, right? R is a PID. And A is in generated. Homomorphisms might be useful here. Think. See, my problem is I don't know anything about A other than it's in generated. It could be just, it could be as ugly as homemade sin, right? I mean, I don't know. But what's one of the things I do know about any module? It's the homomorphic image of a free module. And in fact, more was said in that theorem, since this is in generated, A is the homomorphic image of this. Everybody agree with that? Now, how does that help? Well, so let B in A be our submodule. So what we're trying to do is show that, so A is in generated, so it's the homomorphic image of n copies of this. Let B be a submodule of A. Anybody know what the next step might be? Okay, so we've got B that lives inside here. Let's just look at all the crap that goes to B from here. So we have B that lives in here. Let M be the pre-image of B. Right? What do we know about M? M is now free because now we can apply the theorem because we live inside a free module. And rank M, which is little m, is less than or equal to n. Again, by theorem 3.1.2. Therefore, B is generated by less than M less than or equal to n elements. The images of generators of M. Everybody okay with that? So just pull that thing back inside the free module. This theorem says, hey, that pre-image is a submodule, so it's free and it requires no more than n generators. And now just push that module back onto B. That's onto right, the pre-image is certainly onto B, and that gives you the generators that you need. Questions on that? Okay, let me give you a theorem here that's kind of a fun theorem. I want to keep you for now. And you can use this to get at least part of theorem 13.1.2. Again, this is, I'm only going to prove part of this. Theorem 13.1. Is it? Oh, no, yeah, I'm going to prove all of this. Any finitely generated torsion free, and this means that AT is 0, module over a principal ideal domain is free. Okay, so let me kind of go through the fact that we do need the words that I have up there, right? So if you have a module with torsion in it, it's not going to be free. Let me give you an example. Z6 has torsion in it because 6 times anything in that module Z6 is 0, right? No way is Z6 free, right? Because Z6 as a Z module has no linearly independent subset at all, right? So torsion free seems pretty, we're gonna need that, because otherwise if you've got a module that's got torsion in it, you can't really represent them with a basis, linearly independent one. Finally generate, that's got a little more subtlety to it. Can anybody think of a torsion-free module over Z that is not free. So I want it to be torsion-free, a Z module, so it's a Venn group, anything you like, that's not a free Z module. And I think you actually may have an example like this earlier.
It's a matrix right now.
Well, I mean, so any matrix. So you're talking about a module, so you're going to think of it as a group with a Z action on it, right? So by multiplying the matrices by scalars.
Right.
But the question is where are your entries from? So my answer to your
Z.
no, that'll be free.
R.
Yeah.
What's a torsion again?
Torsion means so we say that I need to name one that M in M is a torsion if there exists a non-zero R in R such that R in equals zero. So it's just something that's killed by a non-zero element. So if what we're talking about are Z modules, the torsion elements are precisely the elements that have finite order. Yes.
Would it be a matrix ring and it make just a matrix under addition, so a matrix ring without the multiplication, and you have would it be your entries are in the reals?
Yeah, but what do you need a matrix for?
So
That's not helping your cause because like if you have, for example, 2 by 2 matrices,
right,
that's just spreading it out.
right.
So why don't you just, yeah, do you have a,
It'd be like over the rationals or the reals, because then they can like become one and cancel each other out.
that's right. So the rationals is actually that, so the reals will work. It's easier for me to explain the rationals perhaps because the rationals are not a free Z module.
Right.
And the reason why is it's easy to prove that the rationals are not isomorphic as a Z module to one copy of Z, right? Because suppose that you have Q is isomorphic to Z, so there's a homomorphism phi from Z into Q. Well, let's say that 1 goes to Q, right? Now this telling me where 1 goes tells you where the whole group goes because it's a cyclic group, right? So 2 goes to 2Q and -1 goes to -Q and so forth, right? It is impossible for that to work because it can't ever be onto, right? So whatever Q is, how are you going to cover 1/2 Q, right? So that means Q can't be 1 copy of Z. So it has to be more copies of Z, right? Which makes sense. But if you remember, one of the things that we talked about earlier is if you have any 2-element subset of the rationals, it's linearly dependent. So there's no way you can form a basis that's bigger than 1 element. And since it doesn't work for 1, you're done. So Q is not, this is an example for it's torsion free, but it's not finitely generated and it's not free. But this is a groovy theorem. And you can use this to sort of get this, the finite case of this, I should say. Yes.
How is how is it yeah, how is a module torsion free if zero's always in it? Like when it's
Oh, right. Okay, that's a great question. Torsion free means there's no non-zero
Okay.
torsion elements. Yeah, that's a point. Okay, so let's prove this because this is kind of and I like the proof of this too. So we did say that So let A be our module. And A is generated by x1, x2, xn. And I think I might need this notation later. I'm just gonna denote this set of generators by capital X. So that's just my generating set. So this is a key thing. Since A is torsion free, no torsion elements, each singleton set what's the matter with you? Each singleton set xi is linearly independent. I don't think that can be tolerated any further. Okay, right? Because as a singleton set, each one of these is linearly independent, right? Because if Rxi is 0, that means R has to be 0 because it's torsion free, right? So what does that mean? Well, so we have some linearly independent subset of capital X, so there must be a maximal one. So let's extract this. Let's say reordering, if necessary. We extract a maximal linearly independent subset x1, x2, up to xk subset of X. Right? So, and at least K is at least 1 because we know that the singletons are all linearly independent. So let's let F so what's generated by that linearly independent set is a free R submodule of A. So that linearly independent, that maximal linearly independent set generates some free submodule of A. And let me point out, if F equals A, then done. Right. So for example, if the entire set x1 up to xn is a linearly independent set, then A is all of F, and we're finished. What if not? Well, if not, then there's an xj there exists j with and xj is not an F, right? So for each j, Okay, for each such J, there's, RJ, such that. Um. Oh, these, I'm gonna double index. RJI. Um. Why is this?
Dr. Coconut,
Mhm.
for clarity, can we have like a negative in front? Because this comes from the linear dependence relation. Correct?
Well, no, I'm gonna ask you, what does that come from? So I'm making this claim here that, so we've got this maximal linearly independent set, x1 up to xk. Um. If we have some xj that's not generated, by the linearly independent set, one of the original generators xj, then my claim is, that I can find a non-zero RJ such that RJ XJ is a linear combination of that basis. Why is this the case? Why should there be a non-zero such that this, such that it's a linear combination of it?
Because you're assuming that if you add it into the set, it's linearly dependent, which means you can write it as solution.
That is correct, right? So if I take xj and I throw it into this maximal linearly independent set, then it becomes linearly dependent. Right? And of course, the linear dependence, that allows me to assume that sort of j itself is not zero, right? So for each such j, we can do this. For each such j, such as xj is not a linear combination of this. So let's let, take the product of all these. Now, what we have here in R is every one of these RJs. So in particular, what that means is if I multiply that R by, if I multiply R by the set X, then any R times this is in F, right? This is certainly true for X1 up to XK because they're already in F, right? But for example, if X is, I don't know, R sub K plus 1, then this thing has, right, I'm sorry, if we have X sub K plus 1, this thing has a factor of R sub K plus 1 in it, and when I multiply it, it's in F, right? Everybody okay with that? And so in particular, RA is contained in F. So now consider phi, right, from A into F, given by phi of A equals RA. And now I will lean on what I've done earlier, but you can go round circle and prove this another way, as a matter of fact. So notice that this map does make sense because, when you take A, multiply by RA, it's in F, so this goes where I want it to. It's pretty clear this is an R module homomorphism, isn't it, right? Because it's just, basically, it's just multiplying everything by R. Notice that phi is 1-to-1, because if A is in the kernel of phi, this implies RA equals 0, which implies A equals 0 as A is torsion free. So there's where that torsion free comes in. You need that. So phi of A, well, get this way. So A is isomorphic to phi of A because it's 1-to-1 and onto its image, which is contained in F, which is free. So phi of A, hence A, is free.
Dr.
Now, there's, yes,
The onto aspect, we're just, like, how do we know it's onto?
we don't.
Okay.
It doesn't matter because it's a submodule or free module. F is free,
Right.
and this is isomorphic to a submodule free. So I'm leaning back on that earlier theorem that we had. If you have a submodule free module, it's free. So phi of A is a submodule, it's a free module, so it's free. And it's
Oh, okay.
let me point out, we did see that there's counterexamples. If you throw out torsion free, and if you throw out finitely generated, and you can see very clearly, I think, where this comes up. The torsion free was needed right here, right, for this map to be 1-to-1, and you're gonna have a hard time implementing this if there's infinitely many RIs to consider, right? And that's definitely a problem. Yes.
What's the bottom index on the R equals product?
Oh, I'm sorry. J equals K plus 1 to N. Okay. Corollary. So let me rip this one off. This is, and next we'll do the big theorem next time. So here's a corollary, and this is basically the parts that you saw. If you were in 4120 or somewhere else, and you saw the fundamental theorem of finitely generated abelian groups, you probably, well, there's this piece that's a bunch of copies of Z. And then there's this finite piece, and you can break this finite piece up several ways. Here it is, and it's more general form. Let A be a finitely generated module over PID. Let A be a finitely generated module over a PID R. Then A is isomorphic to F sub torsion. Then A is isomorphic to F AP, where F is free and finitely generated. AT is torsion module, submodule A. And and of course also finitely generated, and F is isomorphic to A mod AT. What I wanted to say. And just so you never thought that exact sequences would do anything. Yeah. Um, So, um. So, okay, let AT be the torsion submodule of A. The torsion submodule is a module like this. And this is projection, right, where you take A to the coset A plus AT. Everybody okay with that? Everybody cool so far? Now, note. A mod AT is torsion free. See if you can prove this, it's not difficult, but A mod AT is the torsion module, A mod AT is torsion free. That's not too difficult to show. And finitely generated. So A mod AT is free. Agreed? Because that's the previous theorem that we had, A mod AT, is finitely generated torsion free over PID is free. So projective. And since this is projective, the sequence splits. Therefore, A is isomorphic to the bookends. AT direct sum A mod AT. And this bit is the free bit. Okay, any questions on that? Any questions? All right, well, put that in your pipe and smoke it, and I'll see you guys on Monday. Oh, the math club today ought to be kind of interesting. I don't know if you read the abstract, but basically this British physicist back in 1950 watched publicly released movies of the Trinity tests. And the yield on the atomic weapon was classified information. And just using unit analysis, watching the movies with Length scale, he figured out the yield of the atomic bomb, which is kind of cool.
You've given this one before, right?
Yeah, but it was like in 2022, I think.
Yeah, the first week I said Tobruk.
Really?
Well, no, I just remember, it was like.
I have students who remember my math club talk from 3 years ago. I mean, I thought nobody was gonna see this.
Well, no, it was like you talked about it like in your linear algebra class. I don't think I win, but I remember. I'll probably be there next one.
That's funny.
You didn't have to tell me you didn't go. He would have forgot because September 2022.
I was gonna say, how do you get it?
Yeah. Just like, I don't know why.
We got this.
It is a very.
I'm also about to.
Thank you, Dr. Gordon. I'll be on Saturday later.
Yeah, I'll be up there today. I gotta stop and see.
What I was gonna say
Yeah.
is that I low-key broke up with my situation today.
I saw you on the bus Wednesday.
Yeah, you did.
They need a sandblast to make this off.
Thank you.
I'll see you guys in a bit, probably.
But yeah, right with us. Like.
Jesus Christ. What the hell, man? This is just. Please.